Okay, let's go back to 1600, 400 years ago, when William Gilbert, a scientist, English scientist, deduced that the magnetic field of the Earth was actually an intrinsic property produced inside the Earth itself. He did this by looking at the direction of the field around the planet, as much as he could at the time, and comparing it with the direction of the magnetic field around a uniformly magnetized sphere of lodestone, which he called a terrella. And so he deduced that the field was inside the Earth. At the time, the only known source of magnetism was permanent magnets. And so that's what was generally assumed was inside the Earth at the time. That was 400 years ago. We've come a long way since then. Since then, there have been successive discoveries that have enabled us to build on that. And the first was after gravity had been discovered. It was worked out that the Earth had a dense, iron-rich core at the centre of the planet. Later, it was discovered that that core was liquid. So we have a liquid, iron-rich core. We learned that the centre of the planet was hot, very hot. So that core is liquid, hot, conducting fluid at several thousand degrees. Shortly after that, it was discovered that permanent magnets were not the only source of magnetism. Electric currents also produced magnetic fields. And shortly after that, Faraday discovered that magnetic fields, if they were changing in a conducting medium, would produce electric currents. And so we have the loop of electromagnetic induction, which can form a dynamo, a self-sustaining dynamo. So by the beginning of the 20th century, it was suspected that a self-sustaining dynamo in the liquid outer core of the planet was what produced the magnetic field. So the time variations of the core field are typically long-term. And in order to investigate those, we need what we call paleomagnetism. Paleomagnetism capitalizes on nature's natural magnetic records. The records that are imprinted in rocks and in sediments at the time they're formed. So a volcanic rock cools, and as it cools through what we call the Curie temperature of the magnetic minerals, it becomes magnetized in the direction of the field that it's in at the time it's formed. Sediments, the grains that make up a sediment as they fall through water, or air even, are oriented in the direction of the field so that when they become compacted in the sediment, they carry a record of the field at the time the sediment was formed. And so we can use these records to go further and further back in time if we can date the rocks and the sediments. And that's what paleomagnetism is. So, about 100 years ago, a Frenchman, Bruns, found some rocks, volcanic rocks, in the Central Massif area of France, which were magnetized not in the direction of today's field, or the field of 100 years ago, but in the opposite direction. And he concluded that the Earth's magnetic field at the time was in the opposite direction. Few people believed him at the time. It seemed so surprising that the Earth's magnetic field had been in the opposite direction. These rocks were about 7 million years old. That it actually took nearly 50 years before the Earth science community accepted that the Earth's magnetic field had changed its polarity many times in the past. We find that rocks of a particular age are either normal, as the field is now, or reversed. And so there appear to be times in Earth's history when the field has been normal polarity or reverse polarity. We can find sequences of sediments that go through several reversals as we go through time. Perhaps the most surprising and significant record of polarity reversals, though, is on the sea floor. At the mid-ocean ridges which run down the centres of many of the Earth's oceans. And so we have made for us something like a barcode, if you like, of normally and reversely magnetised rocks, symmetrical about the mid-ocean ridge. The last polarity reversal was 800,000 years ago. Between then and now, we've seen several periods of time when the field looks as if it was trying to reverse, but didn't succeed and came back to its original polarity. We call those excursions, and they look like aborted attempts of the core to reverse. So those excursions, there are about 5 or 6 in that 800,000 year period. The most recent is 41,000 years ago and is the most studied and well known. It's called the La Chambre excursion. Between reversals and excursions, the field is still continuously changing. It's continuously changing in both its direction and its strength, and the pattern of those changes is very complex. And those continuous changes we call secular variation. But they have timescales that vary from thousands of years to hundreds of years to tens and even years. Anything shorter than a year, though, we don't detect through paleomagnetic records. We don't see at the surface of the Earth because they don't make it through the insulating mantle, which is about 3,000 kilometres thick. So that's the spectrum of changes of the internal, core-driven, geodynamo-driven field that we see at the surface of the Earth.